are in July 2016 in front of the EDSAC replica when the commissioning work to get the machine working is reaching a very interesting stage where we're attempting to integrate together some of the subunits which have already been tested individually, and this integration part of the work is where we really get to grips with commissioning the whole system. Our current objective is to get an instruction working, to fetch an instruction from the store, decode it and execute it, and then get ready for the next instruction. This is the central control, the coordination of all operations in the machine, a vital part of operation of the machine, and the first one where we're doing the integration testing.
This unit is the unit that produces the initial program to run on the computer before it can actually read in the paper tapes on the paper tape machine. These are standard post office unit selectors, and these four contain the data wired on the pins. The end one controls the operation of these four. When we want to start the machine, we simply push the button, one button, and these rotate round and sequentially put streams of data into the computer. At the end, the computer is now running and ready to accept paper tape.
Central to any computer is a time system, a central source of clock pulses, which are provided on this machine by this chassis here, which provides clock pulses at roughly 500,000 per second. The chassis we're now looking at are the powerful cathode followers which drive signals over the machine. And those clock pulses are distributed to synchronize the way everything works. In addition to that, an important part is to have some pulses which tell us where we are within a word or whatever unit we use. In our case, 36-bit words. We need pulses which tell us where we are within the word. And these chassis here divide the clock pulses by 36 to give us one pulse for each digit position in a word.
The yellow trace is the clock pulse generated here, distributed over the whole machine to keep everything in time.
So Peter, what we can see here is the clock pulse, very regular, running at 0.5 megabit per second, with the selective digit pulses, the blue ones below, and we can see that there is a sequence of those pulses, 36 in fact, within a EDSAC word, and those are used for selecting individual digits in a word. While we're here at the front of the machine, it's worth reminding ourselves about the main store of EDSAC. Half of the main store is housed in these two racks here, both identical, and the important parts are these 1, 2, 3, 4, 5, 6, 7, 8 chassis. Chassis 1, they're called chassis 1. There's another 8 there, and these are to recirculate the data which is remembered in acoustic delay lines. We call them tanks. The original machine had mercury tanks, 5 feet long. We use that nomenclature. It's a tank which has got acoustic pulses. In the case of the main memory, 576 pulses running down the tank. We're going to use wire delay lines because they're safer than mercury, but while we're waiting for those to be finally completed, we've got little semiconductor units which we'll see later. So essentially what happens in here is that each of these chassis 1s is associated with one tank, and the data comes out of the tank in a feeble form. It's regenerated and retimed in the chassis 1, fed back into the tank, and while the machine is switched on, the data goes round forever in the tank and the chassis 1. Repeated 8 times in this rack, repeated 8 times in that rack, and similarly at the rear of the machine. In between the 4 chassis 1s are these chassis here, which are to do with choosing which tank we currently want to work with, selecting it and having gating to move the data from a particular tank in or out of the machine. So essentially that's the main store of the machine, half of it. Here we are at the rear of the front row with the 2 memory racks here, The two in the rear row are over there. And the first thing to notice is these two coax cables, which lead to one of the wire delay lines, which is being tested using this chassis 1. And that's the principle of how they'll all be connected using these coax lines. However, what is interesting for us at the moment is that this is a semiconductor tank, if you like, a little bit of semiconductor circuitry which Nigel Benny designed in the team, and that enables us to store 576 digits as though we were connected to a tank. The chassis 1 interfaces to this, and so that all behaves normally. It's just that its tank is semiconductor and is reliable from that point of view.
We've used some modern technology to generate some pulses to assist with the commissioning or to expedite commissioning. The processor chosen was an Arduino. This particular test box that we have is dedicated to generating the program sequences that go into the tanks or delay lines. That's the data Chris can see on the VDUs.
You can see the 3 cathode ray tubes displaying certain registers, but in particular this central tube is showing the contents of one of the memory tanks. At the moment that one is empty, and using Tom's signal sequence injector we can load a program into that memory tank, and in this case it's part of the initial orders, and if Tom can now inject, we should see the program has appeared in the tank and displayed on this tube here. The tanks are selected by means of a switch, and we find they're empty because they're not connected. This is the only one connected there. And this display unit is currently switched using this switch to that tank, so we can see the contents of the tank displayed with all the instructions in there. 32 instructions on 16 lines. We're now here in this area where the system integration is taking place, that part of the commissioning, the early system integration, where we're trying to get various subunits to work together. The task we have is to try to go through all the steps that are required to execute an instruction. The master control of that is these 3 chassis down here, the master control unit. And that works closely in coordination with the co-instance unit, which is most of this equipment here. And the idea is for the MCU, the master control unit, to ask for an instruction from the memory, to decode that and to decide on the basis of that which operand we need. And so it asks for the operand from the memory and that complete, and then the information is sent to the arithmetic unit for completion. Those are the sort of basic steps in executing the instruction. Now, to assist in that, this equipment has got 3 important key registers holding short numbers. These are little memory tanks, similar to the ones we've been talking about for the main memory, but they're short tanks which only hold 18 bits in this case. In fact, there are 6 other tanks in the machine, mostly in the arithmetic unit. So as well as the 32 long tanks, we've got 9 other shorter tanks, 3 of which are here, and they're the main primary registers for control of the machine. The first one is the counter tank, which I think is this one. That's holding an 18-bit number. This is a half adder which the number goes through before going back into the tank. And the point about a half adder is that it's unlike a full adder, it's much simpler because it only has to add a single 1 at the least significant end of a word. It doesn't need to add 2 long numbers together. And so it's simpler, it's a half adder, and just one chassis is enough to do that in conjunction with the memory tank. And every time we add a 1 at the bottom of the word, that increments the number in the tank. So the counter tank is having its count added, incremented every minor cycle, every 18 bits. And consequently, the number in the tank, 18 bits long, is counting up like fury every 36 microseconds, and very rapidly gets to 250,000 and then starts at naught again. And we can see that counting up going on the oscilloscope. We are only interested in the least significant 5 digits, the least significant 5 bits of that count, because those 5 bits are counting from 0 to 31 and back to 0 and 31, if we just consider those 5 bits. And those bits are essentially enumerating the addresses within one long tank in the main store. So they are keeping count of where instructions are in the main store. If the number in the counter tank is 25, it means that the instruction in location 25 is coming out of the tank. So that's part of the address mechanism for getting information out of the memory. That's the counter tank. Now, similarly, there's a tank, a short tank, with its own half adder, and that adds 1 into the bottom of its count every time an instruction is executed. So that tank is keeping count of instructions within a program. It's what in modern terms we'd call a program counter. It's the sequence control tank. And the number in that tank is telling the rest of the machine, this is the address of the instruction we want to obey. And then lastly, there's one more tank here, which is just a plain register with no adder or anything, called the order tank. And that tank holds the currently being executed instruction. Once the instruction's got out of the memory, it's put into the order tank, and there it stays going round and round every half word, and so is available for any purpose that we may need. Now, we can now go back to considering execution of an instruction. The master control unit starts it off by saying, I need an instruction. And it says to the coincidence unit, which is here, kindly get the next instruction out of the store. Well, we know the next instruction is a number held in this sequence control tank, a 5-bit number. So that 5-bit number going round and round in there is continuously compared with the incrementing number in the counter tank, which is going round and round and incrementing. And eventually, the two numbers will agree. And when they agree, that's coincidence, we know that the instruction that we want, designated by the sequence control tank, is coming out of the memory and can be brought in and put in the order tank. So you've got this concept of numbers circulating. Eventually there is coincidence. That triggers the coincidence unit to put the extracted instruction into the order tank. And there it is, ready for stage 2 of executing an instruction. That's the order that we want to obey. In a serial machine like this, where information is flowing on single wires in a sequential series, it's nevertheless very important that some of the information is held steady so that it can open gates and connect registers and so on. So we have a problem of converting the serial stream of data on a very economical single wire into a parallel piece of data which is held steady. And this rack here holds the static units which are fed with serial information from the memory tanks, for example, and then hold that for the 72 microseconds or however long it takes to control the gates. And these units here have got, for each chassis, they hold just 2 bits. So here we've got a conversion from an economical serial one-wire system to a rather elaborate and expensive parallel system. But that's necessary in a serial machine like this, some mechanism such as that. Now then, this bit here is the bit which holds the operation code within an instruction. This is the bit which holds the information that says it's an add, a subtract, an input, it's print this or whatever. So that's the thing which determines the function of this particular instruction. So we've got a decoder, an encoder, and that then controls the rest of the machine. And so that part That's all to do with determining what particular function we need in this machine.
John is operating the engineer's test switches at the moment. This is a means by which we can inject specific orders into the machine for repetitive execution. And you can see the whole word here that's stored in the order register. The rightmost 5 bits are those bits which are used to decode the order. When John sets one of the switches down, you'll see a specific bit disappear. So he's able to control individual bits in the order tank by that means. Okay, if you could set all down except F15 up. So now we see the order set with just bit number 15 set on, and that corresponds to the R instruction, which is the right shift instruction. The right shift instruction is very important because it's a very simple means by which binary computers can divide a number by 2. Simply by moving all the bits to the right, you divide the whole number by 2, and we can perform that very fast using electronics entirely.
We're now at the rear of the machine so that we can have a look at the rear of the middle row of racks where the control system is, where this key part of system integration, the commissioning of the central control part of the machine, is taking place.
This particular test box is generating pulses for testing the master control unit, and so it essentially assists James and John in testing their subsystems.
And of course we work at the rear, on the rear of the chassis, because we can access all the signals easily with our oscilloscope. Here the system integration of trying to get a complete instruction, all the steps of an instruction working, that's taking place with James and John working on their respective subunits in order to make this sequence of steps work together.
John and I are testing the MCU, which is the master control unit of the computer. The master control unit consists of 3 chassis at the bottom of this rack on the right and controls the major states of the machine, which are fetch the next instruction, execute the instruction, and perform a memory rewrite if that's required for that instruction. It then cycles round to the fetch state again, and it does this endlessly, very rapidly, executing instructions at approximately a rate of 650 per second.
I've got the mains disconnected. Just trip the HT, will you? That's always a reason why things don't work. Usually it's because we haven't switched it on.
The number of times we'd spent an hour chasing around a bad signal to find that the fuse on that chassis was blown an hour ago. And that's the reason.
Right. So there is your nice clean.
Oh, that's pretty now.
Takes to connect things.
Yeah, the yellow trace at the bottom is the S1 signal from the master control unit requesting the coincidence unit to obtain the next instruction from the location pointed to by the sequence control tank.
So James, you've got a simulated end pulse coming out of Tom's red box, representing what the ALU would have done had we got it here in these empty racks. Can you tell me what that end pulse does in the MCU?
The end pulse instructs the MCU that the previous instruction has been completed and the system is ready for finding the next instruction in memory. The yellow trace shows the end pulse signal, and the S1 signal output is on the blue trace at this spike here.
That's the S1 pulse going over to the coincidence unit, as you've explained, and presumably that just tells the coincidence unit to fetch the next instruction. That's the R pulse come back from the coincidence unit, and what does that tell us?
The R pulse comes back to say that the order has been loaded into the order tank, has been decoded through the order decoding system, and is available as control signals from the recoding of those signals.
So having got the R pulse, what does the master control unit do with that?
The R pulse causes the commencement of the second stage of the cycle, which is to send out an S2 signal to the coincidence unit to fetch and decode the operand part of the instruction.
Can we see the S2 being made?
Yep. The S2 signal is a problem at the moment for us because we're seeing one half of a diode AND gate go high. The S2 signal should come out of that as a single large spike looking similar to the S1 signal synchronized with digit 0. But in fact we're getting multiple signals. So we've got some further work to do to try and find out the cause of that and fix it.
Okay, we've seen the progress so far on this system integration, in particular some of the problems of trying to get the whole loop of subunits working together harmoniously. Obviously, as we go through, with faults turn up and they've got to be fixed. So we've seen very good progress on this finding the sequence or establishing the sequence of steps through execution of an instruction. But that's what system commissioning is all about. Find the faults and fix them. And we're in the throes of doing that. I think it's interesting to see also that the technology that EDSAC used is rather unlike modern technology where you can join things up and they work. The EDSAC technology, often when you join things up, they don't necessarily work and you've got to tweak something to make them work. And I'm sure that's what happened on the original machine when Rennick probably spent most of 1948 and 49 actually doing this sort of tweaking work. So we're reenacting that in a highly replica-like way. Now, change of gear here. We've been looking at the work in progress, and now just to fill out, we should say something about the further pieces of work which have to be done. So round here, in this rack, you've already seen the initial orders unit here. That's placed in that position because it's convenient for engineering purposes at the moment, but it will finally live up at the top of this rack with the engineer switches down below it and so on. So most of this down here would be empty. However, what goes in there are the control units for the input-output equipment. Looking over here, there's a teleprinter and a tape reader. Now these actually are not exactly what we're going to use, but they're very similar. We're using something which is somewhat older than these. So we have a paper tape reader to read the paper tape into the computer and a printer to print output from the computer. And the control units for those are going to go in here. Both of those are currently being made and tested in someone's home in Cambridge. I think the paper tape reader is probably working and soon will come in and be fitted there. The printer, there's some more work to do. So that's more work to do to fill in that rack. The last thing we want to see is nothing to see. In the back of the rearmost row here are 3 empty racks. This is where the arithmetic and logic unit, what the pioneers called the computer, will fit in, and that equipment is all in Nigel Benny's house in Cambridge, again more or less complete and tested. He's got a few more things to tweak, but all the chassis which go in here, around about 30 chassis, will go into these racks real soon, and that will nearly complete all the hardware of the machine. The arithmetic unit with the accumulators, the multiplicand, the multiplier, and all the ancillary stuff, which the work of the control units prods. The control units send signals to this, and that will be the last stages of commissioning. So, watch this space. How corny.